Uh, Hello, Dr. Sakwa. I know if you're speaking, you are on mute. Yes.
Oh, yes. Thank you. Okay, welcome. So let's look at a concept of rings. We've been looking at groups. So we want to begin at looking at rings. Groups, we looked at so many things about groups, including hashing to groups. If you have data and you want to hash it to an element of a group, we've done that. So today we want to look at the concept of rings, and it's very much related to groups. The only difference between rings and groups is that while groups will be looking at one operation, while groups, you see groups, we talk of a group being either additive or multiplicative. That means at every point we are dealing with only one operation. But rings, we'll be dealing with the two operations at the same time, addition and multiplication. So that is that's only difference. That while groups will be looking at one point, we're looking at an additive group, and then another point we're looking at a multiplicative group. But when we talk of a ring must have these two operations at the same time, addition and multiplication at the same time. Now, just before we look at rings, of course, I've given the where we'll be applying it in a real life situation, and we look at those applications. And I'm saying that rings, particularly those of integers and modular arithmetic, are very important in number theory and in cryptography, primarity testing, and so on. So rings will be very important. We shall see how they're important in cryptography. And of course, that is our main interest. How do we use rings in cryptography to secure information? So that we'll be looking at that. Now, I've listed some of the ways we'll be applying it in cryptography. I've said that in cryptography, we'll use it in RSA encryption. We'll also use it in lattice-based cryptography. And also, yes, in lattice-based cryptography. So we'll see how they're used, especially when we reach on lattice-based cryptography. We'll see. Of course, we'll go back to RSA and see again how rings are used there. So those are part of the ways to be applying it in cryptography. There's also homomorphic encryption. We also apply rings in homomorphic encryption. You remember the other time we were trying to do homomorphic encryption. This, just to remind us, this is where you have encrypted the data and you allow that a second encryption can be done on this data without necessarily having to decrypt it. So rings again are very much important there. So let's now define a ring. Let's define a ring. Of course, I've just been looking at overview of what where we apply it and so on. A ring is an algebraic structure, just as a group. It's made up of a set. A set is just a combination of objects. So a ring is made up of a set and two binary operations. And those two binary operations are addition and multiplication. So as I said, a ring is different from a group because a group, when we talk of an additive group, the operation is just addition. And then when we come and talk about a multiplicative group, the operation would be multiplication. But when we talk of a ring would have all these operations at the same time. We'll have all those operations, addition and multiplication at the same time. So that's what I say. So this is a set. It's a set. And apart from this set, we have these two operations, addition and multiplication at the same time. So that's what we call a ring. And of course, it must fulfill some conditions. Just as a group fulfills conditions, a ring also must fulfill conditions. One of the conditions is that it must be a group, it must be an abelian group. For it to be a ring, it must first of all be an abelian group. You remember what an abelian group is? An abelian group is a group which is commutative, such that if you have two elements of the group A and B, then it will be true that AB will be the same as BA. This is what we call commutativity. So a group that fulfills this condition is called an abelian group. So therefore, what we are saying is that facet, together with these two binary operations, to qualify to be called a ring, first of all, it must be an abelian group. It must be an abelian group. So the conditions I've put here are the conditions that are satisfied by an abelian group. An abelian group, and let me just repeat, I said, for this R, which is a set, together with these two binary operations of addition and multiplication, to qualify to be called a ring, one, it must be an abelian group under addition. It must be a group, abelian group under addition. And just say what an abelian group is. Now, so the conditions I've listed here, 1, 2, 3, 4, up to here, no 5. These are conditions we already know, conditions that an abelian group fulfills. The first condition that an abelian group fulfills, and we are talking about an abelian group under addition. So the operations here up to here is addition. So the first condition that an abelian group must satisfy is that it must be closed. So the property of closure. In other words, you pick any two elements from this group, and when you add the result, when you add them, if you pick two elements and add them, the result must be a member of that group. The result must be a member of that group. So for instance, if I have under addition, let me say if I'm dealing with the Z6, for instance, and we know what the elements here are, 0, 1, 2, 3, 4, and then 5. So what you're saying is, if we pick any two elements, 2 and 3, and sum, the sum will be 5. And you can see that 5 is a member of this group. 5 is a member of that group. So that is a property of closure. We're saying that it must be an abelian group, a ring. For it to be a ring, it must be an abelian group under addition. And so for it to be an abelian group under addition, one, it must fulfill the property of closure, and then it must fulfill associativity. And we already know what these ones mean. You pick any three elements and add, if the bracket, just change the position of the bracket, the result must be the same. Then the other condition that a group must fulfill is that there must exist an identity element. There must exist an identity element. And since we are concerned about the abelian group under addition, the identity element is 0. Such that this 0 added to any element, whether you reverse, the result will be that element. And the other condition that a group must fulfill is that every element of this group must have an inverse. Under addition, the inverse of 2, of course, will be -2, and so on. And so that is what I have written here. Let me admit some members here is okay. Now, so we say that it must be a group it must fulfill that every element has an inverse. And then lastly, what makes it to be an abelian group is the property of commutativity, which you see here, commutativity, that you pick any two elements and add A plus B, the result should be the same as B plus A. And let me just repeat what I've said to this far. I've said that a ring R, or a set R, a set R to qualify to be called a ring, it must, first of all, be an abelian group and addition. So to be an abelian group and addition, it means it must fulfill these 5 conditions. Now, the other property that it must fulfill to be a ring, that under multiplication, it must form a semigroup. Under multiplication, it must form a semigroup. What we mean by that, what we mean by forming a semigroup is that under multiplication, it must also be associative. Under multiplication, it must also be associative. This is multiplication. We talked about associativity under addition when we were talking about it must be an abelian group. And this time, we are now saying under multiplication, it must be a semigroup. In other words, it must be associative. Then 2 and 3, again, under multiplication, it must fulfill distributive laws, And what that means is this. This is A multiplied by the sum of B plus C. So you distribute this A inside. And when you distribute this A inside, it will be A times B plus A times C. So this is the left distributive law, left. So our scalar is on the left side. Our scalar is on the left side. We can also have the scalar being on the right side. The scalar being on the right side, and then you distribute it inside. When you distribute inside, you have SC plus BC when you just multiply this thing inside. And this is what we call the right distributive law. Now, so if a set fulfills these 3 conditions, then that set will be called a ring. If it fulfills these 3 conditions. The first condition was that it must be a group, an abelian group and addition. And 2, it must fulfill the associative property under multiplication. And then 3, it must fulfill the distributive laws. If it does fulfill those 3 conditions, then it becomes a ring. Now, so what notation do we use? I said a ring is a set together with these 2 binary operations. So this is how we denote a ring. But once we get to know that the operations are addition and multiplication, there's no need of writing it this way. You can just write it as R to mean a ring, and somebody will understand that you mean it, that is a set R together with the 2 operations, addition and multiplication at the same time. So we do not talk of an additive ring. We do not talk of a multiplicative ring. There's not. A ring is just a ring. It already has these 2 operations. We do not have an additive ring and a multiplicative. Like we had an additive group and we had a multiplicative group. We do not have such a thing when it comes to rings, because a ring has those 2 properties. So the addition property, you've seen where it applies. The addition operation. The addition operation is applied here to make it be a group. It makes it be a group, an abelian group and addition. That's where the addition property is used. Then you can see, the addition operation. That's where the addition operation is used. And then the multiplication operation, you can see it's now used here to make it be associative under multiplication. Then we have those 2 operations here for distributive laws. You can see the addition is here and then the multiplication is here. And then we distribute. And again, we have it here. So a ring must have those 2 operations at the same time. So what I was saying is we denote a ring by we denote it this way. But once it's understood that the operation is addition or multiplication, then we just denote it this way. A ring. This is just capital R is not the same as this. You see, this is for real numbers. This is for real numbers, but this one is now just for a ring. So you should not confuse when you see this and think that, you see, this could be a ring, this could be a ring, but now that is when you're talking about types of rings. When we talk of types of rings, maybe we may now talk about this as an example. This just becomes an example of a ring, but we denote using capital R, not this double math R. So my point here, I've said in contexts where operations are understood, mathematicians typically just use R without adding those signs, without adding these operations. In contexts where it's understood that a ring has those two operations, you don't need to always put, but there's no problem. You can denote it this way, you can denote it in either way. You may want just to denote it that way or denote it this way, there's no problem. I've just put this point here for emphasis. I've said, remember the first operation must meet all the 5 properties of an abelian group. And you've seen that the first operation here is addition. It must fulfill all these 5 properties of an abelian group. That's what that point means. And then the other point here, I've said the second operation may only satisfy closure and associativity. That is, the second operation may fail to satisfy the other properties. So what you're saying is, it's not a must that the multiplication operation must fulfill all the properties. It can just fulfill closure and associativity and stops there. There's no problem. But the addition operation must fulfill the first 5 conditions. So the second operation, it can fulfill closure, can fulfill associativity, then it comes far and fulfills distributive laws. So we'll be looking at examples so that you understand how those 2 operations are used. Now let's look at examples of rings. The first example of rings is the set of integers. You know what the set of integers are? Integers are these elements: -4, -3, -2, -1, 0, 1, 2, and so on. These are what we call integers. So the set of integers forms a ring. Remember, it formed a group when you're looking about groups. When you look at groups, it formed a group. It also forms a ring. You can see that, and we'll be proving. I'll show an example to prove that this set is a ring. So in that example, we'll be now wanting to see how it is an abelian group. How it's an abelian group, because that is the first condition that it must fulfill. And 2, we must show associativity under multiplication. And 3, we must show distributive laws. In fact, that's what you show if you have to show that something is a ring. That's what you then show. So this is the first example of a ring. And the second example are these are the rational numbers. The rational numbers, these are the rational numbers, rational. These are the real numbers. And these are the complex numbers. So the rational numbers, the real numbers, and the complex numbers also form a ring. Also form a ring. So those are the examples of rings. Those are other examples. So I hope you know what rational numbers are. A rational number is any number that can be written in the form A out of B, where B is not equal to 0, is not equal to 0. And the only common factor between this A and B is 1. So the GCD of A and B is 1. So when I say the GCD of A and B is 1, it means that these two numbers are relatively prime. These two numbers are relatively prime. Or the only common factor is 1. For instance, 1 out of 7 is a rational number. 3 out of 5 is a rational number. 8 is a rational number because it can be written as 8 out of 1. 13 is a rational number because it can be written as 13 out of 1. So what I mean is the whole numbers are rational numbers. And fractions, where the only common factor is 1, are also rational numbers. So you need to know what rational numbers are. So all fractions that you know, whether negative or positive, and the only common factor is 1, are rational numbers. And all whole numbers that you know, whether negative or positive, are rational numbers. So it means even these integers are rational numbers because the integers consist of all whole numbers, negative and positive. So integers, in fact, what I'm saying, they are subset of rational numbers. They're subset. This would be a subset. So all the members of the integers are contained in the rational numbers. What are real numbers? Real numbers, we know, these are just all the numbers we know, whether fractions or decimals or whole numbers. Those are real numbers. What about complex numbers? A complex number is a number that can be written in the form A plus IB, where I is imaginary. Where I is imaginary. I is imaginary. And I has the property that I times I gives you -1. So in other words, what you're saying, that the square root of -1 is I. The square root of -1 is I. So this is the property of I. So what I mean, numbers like 3 plus I7, these are complex numbers. Numbers like 2 plus 2I, so long as there's an I, is a complex number. Even numbers like 7 is a complex number because it can be written as 7 plus 0I. So that is a complex number. Even 15 is a complex number because it can be written as 15 plus 0I. Even a half is a complex number. It can be written as a half plus 0I. Even 2 out of 3 plus 13I. So complex, what are complex numbers? Even the real numbers are complex numbers. Even these rational numbers, all whole numbers that we know are complex numbers, whether negative or positive. All fractions that we know are whole complex numbers. And in addition to that, numbers which can be expressed in the form A plus IB are also complex numbers. So that is just to assist us know what complex numbers are, what rational numbers are, what real numbers are. But we've said that all these form a ring. They are rings. They are rings. And we can also have matrices also form rings. n by n, these are square matrices, form a ring, and addition and multiplication. Now, we'll then spend time to look at polynomial rings just after this introduction. We'll look at polynomial rings. So these are just polynomials, are just equations that can be written. These are expressions that can be written in the form x raised to some power plus bx raised to some power, and so on. So that is what is called polynomials. But of course, I'll formally define what a polynomial is. And then we'll spend some time to look at it, how to add the polynomials, how to multiply them, and so on. Now, so I'm still looking at examples of rings, and I've said polynomials form rings. And the set of integers mod n also form rings. The set of integers mod n. So set of integers mod n, this is how we write it. If you want, you can also write it this way. The set of integers mod n. So for instance, when we talked of Z8, this is set of integers mod 8 forms a ring. If you want to write this in this form, you can write it this way, and write it this way. So this is with that, they mean the same thing. Set of integers mod n. You can, some books use that, and some books use this. So it means the same thing, set of integers mod n. They form a ring. Now, what we know, let me just explain here. We know that a set of what we've just written, this will form a group under addition, because there's no star. There's no star. But when it comes to a ring, it forms a ring. And you know rings, we're talking about both operations. We are talking about addition and operation, addition and multiplication. So under addition, this will form a group, and we agree, an abelian group. It will form an abelian group under addition. So then you come and then see whether it fulfills associativity under multiplication. Come and see whether it fulfills associativity. And then if it fulfills distributive laws. So we'll come and show that. But we agree that it forms a group under addition. It forms an abelian group under addition. We agree that this forms a group under addition. Then we come and now see, we'll come and see that it fulfills also associativity under multiplication. And then it fulfills distributive laws. Now, what about if it has a star? Does it form a ring if it has a star? If it has a star, you know that is a multiplicative group. So that one will not form a ring. If it has a star here, like that, it will not form a ring. This will not be a ring because, of course, it cannot be a group under addition. This one cannot be a group under addition. So that alone disqualifies it from being a ring. But if we remove a star, it becomes a ring. Because first it's a group under addition, then see if they're fulfilled. Just come and check if they're satisfied. Now let's look at this example before we go to polynomials. Show that this is a set of integers. Show that it's a ring. So what are we supposed to do? We're supposed to show that, first of all, is a group, an abelian group under addition. That's what I was doing. That's what I was doing here. I want to show closure. I pick two elements, And after picking those two elements, I want to see whether their sum is a member of this set. I want to see if their sum is a member of this set. When I take 2 plus that, and I can see that is 5, and 5 is a member of this set. So it means it's closed. I said that you can even check even multiplication and you want to see whether it's closed, but it's not a must that it must be closed under multiplication. But what is a must? That it must be closed under addition. This is not a must. But let's check. Pick any two elements. 2 times 3 will be 6, and 6 will be a member of that set. And then check associativity. Pick any 3 elements and add them. Just to vary the position of the bracket. So when the bracket is here, what you get is 5 plus that, what is 7. And when you change the position of the bracket, that gives you 3 plus 4, that is 7. So 7 and 7 are equal. It means it's associative and addition. And then, of course, there is the identity element. So the identity element is there. And now every element has an inverse, 2 has an inverse, and 4 has an inverse, and so on. Every element has an inverse. So that means, or it's a group and addition. It's an abelian group. So we only need to check whether it's commutative. And that's what I was showing the last here. Associativity, I'm showing it here. This is where I'm showing associativity. Pick any 2 elements and see whether 3 plus 4 is the same as 4 plus 3. Check whether that is true. And it's true for all elements you pick. So it fulfills that, then it's an abelian group. Now to check whether it fulfills associative property under multiplication. Because that is now the second property that a set must fulfill to be a ring. You check whether it fulfills associativity under multiplication. So I picked 3 elements from the set and multiplied. The bracket here gives me 10. Then when I multiply by 4, I have 40. Then change the position of the bracket. This is 8 times that is 40. So it has fulfilled associativity under multiplication. Now the last property, distributive property, is the one I want to check if it's satisfied. I pick 3 elements. I add this, then multiply by 3. So this is same as 7 times that, which is 21. Now, so what I want to show that this part is the same as this part. Just want to show this part on the left side. So the part on the left side gives me 21. What about A times B? In that case, it will be 3 times 2, and then plus 3 times 5. So the first bracket gives me 6, and the second bracket gives me 15. And again, that is 21. That means it fulfills the distributive property. That when you distribute here, what you get on the left side will be the same as what you get on the right side. You can also change the position of the scalar so that you distribute inside. So you want to see whether the left side will be equal to the right side. So I picked 3 elements. So what is inside the bracket is 5 times 5, that is 25. So the left side gives me 25. What about the right side? Because the right side will be 2 times 5 plus 3 times 5. What does it give? So 2 times 5, of course, is 10, and 3 times 5 is 15, and again, that is 25. So distributive property has been satisfied. So what I'm saying is, for you to check if something is a ring, you have only 3 properties to check. The first property, you're checking whether it's a group is a abelian group under addition. And then the second property, you're checking whether it fulfills associativity under multiplication. And then the last property, you're checking whether it fulfills distributive laws. And that is what I've just explained here. That is what I've listed. Now, the last example. This one I had already explained. I had already explained that when you take the set of integers, mod n, with a star there, that consists of elements or integers which are relatively prime to n, then it will not form a ring. It will not form a ring because this one does not include addition operation. It does not have addition. Of course, you can see that it will not form a group. It lacks the zero. The zero is not there, the identity element and addition is not there. So it will not form a ring. So I was just emphasizing that point. This will not form a ring because first, it does not form a group and addition. Now, so we want to spend some time now on the polynomial rings. We want to see how to add polynomials, how to multiply polynomials, and so on. Then from there, we'll see how we can use our code, therefore, to do the same operations. I'm just defining what I mean by a ring of polynomials, or what you can also call polynomial rings. That's what I'm defining. And I'm saying a ring of polynomials refer to a set of polynomials. A set, so if you have polynomials, a set of these polynomials, we shall call it a ring of polynomials. Now, so we'll abbreviate it this way. This is how we'll abbreviate it. A ring of polynomials is just R with this bracket, square bracket, with an X. X is just a variable. X is a variable. This is how we write a polynomial. A polynomial f of x will be written as this. S, these are just constants. These are just constants. Could be 5, this could be even 7, this could even be 3, and this could even be 1,000. These are constants. S are constants. That's why I've said where AI are, these are rings. Huh? That's what I said. I said the polynomials with the coefficients form a ring. The coefficients, these are what we call the coefficients. But they'll be constants. They'll be constants, can be 10, can be 13, can be 20, and so on, the constants. X is just a variable. So this X is raised to a power. This N could be the power, could be 10, and this could be, it's N minus 1. So this is 10, so this would be 9, the power there. And so the next power will be 8, and it reduces until the next power is 1 here. You can see here it's 1. And then this one, it was 0. So when you raise anything to 0, it's 1. When you raise anything to 0, you get 1. So that means 1 times A naught is just A naught. So what we are talking about is something like this. That a polynomial f of x could be something like even 9x raised to 13 plus, may say 8x raised to 12, maybe x raised to 12, n could be not be there. So let's talk of even 7x and even talk of 20. This is an example for polynomial. That's what we call a polynomial. It's just an example. Now, the highest power of the polynomial is what we call the degree of that polynomial. The degree of the polynomial refers to the highest power of that polynomial. So if the highest power is 10, then that polynomial is of degree 10. If the highest power is 7, then we say that polynomial is of degree 7. Let's look at operations on polynomials. So we can add polynomials, we can multiply polynomials, and so on. Polynomials form a ring under usual operations of addition and multiplication. They form rings. So they just act like integers, just the same way integers act. That is what I mean by this, is that just like the way we add integers, we can also add integers mod n. So polynomials can also be added mod n. We can multiply integers mod n. So polynomials can also be multiplied mod n. So they just behave the same way, and we'll be seeing that. We can subtract polynomials. We can multiply polynomials. Now, so we want to begin by adding, and then we go to multiplication, but I've just said that to add polynomials, we simply add the coefficients of the same index. The coefficients of the same index. What I mean is this, that if I had, let me say 7x raised to 2, then 3x raised to 4, let's say, and this is my first polynomial. And suppose I have another polynomial, that let me say 8x raised to 2 plus 14x raised to 4. So what I mean by adding, so if I add f of x plus g of x, then I just be adding those which have like the like terms. For instance, you can see x squared here and then x squared here. So when I add these two polynomials, I get 15x raised to 2. So I add those which are like terms. And you can see x raised to 4 and x raised to 4. So this then will give me 17 x raised to 4. That's what I mean when I talk about adding coefficients of the same index. What about multiplying? To multiply polynomials, we use distributive property, which we've just talked about earlier. But again, I'll show you how that happens. So you use distributive property, and then after that, you collect those like terms together and add them. Collect like terms and add. So what is very interesting is how we'll be doing that mod n. It's very interesting, and we'll be seeing that in a short while. Now, this is just an example, given two polynomials, and this is the first polynomial, an x raised to that plus an minus 1 x raised to that. And this is another polynomial, bn xn, and then bn, and so on. Suppose I want to add this. Supposing I want to add these two polynomials, I'll add those like terms. Like you see, these are like term to this. It's multiplied by xn, x raised to n. So you can see that is my x raised to n. And what is inside is an plus bn. An is plus bn. So just factor the xn outside the bracket. Then you can see that these are like term to this. So because it's x is raised to n minus 1, x is raised to n minus 1. So what is inside is then the sum of this and the sum of this. That's what is inside, and so on. What about multiplication? Multiplication, we just said that we are using distributive property. And I'll show you how that then, this is the formula, but I'll then show you how it works. I've shown here how that formula works. That I have this polynomial and I have this polynomial. So what I do, distributive property says I multiply this first part by the whole thing. Then I'll come and multiply. That's what I've done here. That's what I've done here. I've taken the first and multiplied by the second polynomial. So this part will be multiplied by the whole thing inside this bracket, inside that. Then this part will also be multiplied by the whole thing inside here. And then, and so on. Then after that, we will collect like terms. Now, so what is the degree of the polynomial f of x? This polynomial here, the degree we say is the highest power. You can see this is the highest power. The highest power is n. So this polynomial, its degree is n, the highest power. And if we were to add them, if we were to add this polynomial and this polynomial, the highest power would still be n. When you add, the highest power would still be n. But when you multiply two polynomials, the highest power becomes the highest power in the first polynomial plus the highest power in the second polynomial. So the highest power in the first polynomial plus the highest power in the second polynomial. That sum becomes the degree of the product. And that is what I've explained here. That if you have these two polynomials, then their degree will be the highest, so you consider, if you, okay, so if you are summing them together, if they had different degrees, then the highest of the two degrees becomes the degree of the sum. If they had different degrees, but in my example, both had n and n. So if n and n is just the same, then the degree of this sum will just be n. But if they had different degrees, supposing one, the highest degree or the highest power was 3, and this other one, the highest power was 7, the degree of the sum will be the highest of the two degrees. But for multiplication, you take the degree of the first plus the degree of the second. That becomes the degree of the product. Now, I think examples will make that clear. Examples will make that clear. So the first example says, I have these two polynomials. Consider two integer polynomials, f and g. In this ring, this is a ring. Once you have, this is a ring of integers. Okay, these are polynomials. Integer polynomials. These are integer polynomials. That's why I've said this. So when you do this, and then this will be a real number polynomials. Now, but the most important thing is this. The first polynomial is here, and the second polynomial is here. The question is, find the sum and the product of these two polynomials. After finding that, also find the degree of the sum and the degree of the product. Before we go there, let's just look at the first polynomial that we have. The degree of this first polynomial is 3. Because 3 is the highest power. And the degree of this other polynomial again is 3. 3 is the highest power. So that's what I mean by degree. The highest power. Now, so we want to sum. Summing is very easy. We just sum those which have like terms. Like, for instance, you can see this and that are like terms. So when you sum those two, you get -4. That's what you're seeing. -4x cubed. And then this is a like term to that. And when you sum that, you get -21 x squared. This one does not have a like term. So in fact, it could have been 0. Maybe it's 0. x squared. So when you, no, x, it is 0x. So when you take 0x plus this 12x, you just get 12x. And then the constants are like terms. When you add negative 13 plus 10, what you get is negative 3. So this is how we sum these polynomials. It's very easy. Summing polynomials becomes very easy. So we've done the summation. We now want to do a product. But before that, you can see that the degree of this polynomial is 3. You can see the degree is 3. The highest power is 3. And that's what we are saying here. The highest power is 3. And that's what we said. We said, if you have these two polynomials, the degree of the sum would be the highest degree of the two. So you can say, but these two coincidentally have the same degree. Coincidentally, they have the same degree. So that same degree becomes the degree of the sum. But supposing one had a degree of 4, another one had a degree of 3, then 4 would have been the degree of the sum. 4 would have been the degree of the sum. Now let's get the product of these two polynomials. The first polynomial is here, and the second polynomial is here. So what we said, we just distribute, use distributivity. We multiply this by all of these. So 3x cubed times the first part, which is negative 7x cubed, gives you negative 21x raised to 6. Remember the law of indices, that if you have a raised to m multiplied by a raised to n, the product will be a raised to m plus n. That's the law of indices. So the powers I just added. The powers, you can see 3 plus 3 gives us 6. And now we had that product gave us negative 21. Then now this, by the next element, the next element is negative 6x cubed, no, x squared. So 3 times negative 6 gives us negative 18. Then x cubed times x squared gives us x raised to 5. You add the powers. Then we do the same. This with the next gives us 30x cubed. So we are done with 3x cubed. We are done with 3x cubed. We got the next element. We're just using distributivity. So now the next element is 15, negative 15x squared. Negative 15x squared multiplied by each of these. So the first one will be negative 15 times negative 7. Negative times negative is positive. 15 times 7 is 105. X squared times x cubed will be x raised to 5. That's what you do for all of them. So you do this with multiply with all of those. Then come to 12. That's what I'm doing here. Come to 12. 12x times negative 7x cubed gives you negative 84x raised to 4. Then 12x times this would be negative 72x cubed. So you do the whole thing. Then you come to the constant. This constant multiplied by the other group, the others polynomial. Multiply negative 13 by each of this, and you get that. Then after that, just collect like terms and sum. Collect like terms and get the sum. So you can see, for instance, that this x raised to 6 has no like term. You cannot see it. You cannot see anything that is raised to 6 here. You cannot see. So we just remain this as negative 26x raised to 6. Then what about x raised to 5? You can see it here. It's the only one. So negative 18 plus 105 gives you 87, x raised to 5. Then come to x raised to 4. X raised to 4, you can see it here. You can see it here. And there's no other. So these two added together gives us 6 x raised to 4. Then come to x raised to 3. You can see it here. X raised to 3, and there's another one here. And then there's another one here. And so on. So you collect like terms and add the like terms. So it's very easy multiplying polynomials. It's very easy multiplying polynomials, and that's how we multiply them. And the degree you can see is the sum of the two degrees. The sum of the two degrees. The degree here was 3, and the degree here is 3. So the sum is 6, and that's what you're seeing. That's what you're seeing. It becomes the degree there is 6. The degree is the highest power. Now, so it's now easier. You'll not go through this because it's very easy how we add and how we multiply polynomials. So of course, for addition, you can see this one, x cubed. It has no like term here. So we just remain as x cubed. And then x squared, it has a like term. So 5 minus 2 will be 3. So very easy. And then 4x, there's no like term this other side. So it remains. And then 2 has a like term, the constants, that gives us 7. That's how you add. And then multiplying again, we just do the same way we did the early example. The early example, you do distributivity. Then after that, you add the like terms. Now, what is interesting is now is how we do it mod n. That's what I want to spend a few minutes. How we do it mod n, how do we add mod n, and how do we multiply polynomials mod n. I want to do this mod 17. I have this polynomial, and I have this other polynomial, and I want to get their sum mod 17. So we just do the same thing we've been doing. Add like terms and reduce them mod 17. Reduce the coefficients mod 17. That's what we'll be doing. You add like terms. After adding like terms, if they go beyond 17, reduce them mod 17. So let's see. This is a like term to this. So when you add this, you get negative 4 x cubed. Of course, we are doing this mod 17, but we want this to be positive. So to get it positive, just add 17 to it, the remainder. When you add 17 to this, you get the remainder there is 13. That's what I have, 13x cubed. 13x cubed. And then again, this has a like term there. When you add this, you get negative 21 x cubed, x squared. And we are doing this mod 17. This number is negative, so we want it to be positive. So when you add 17 to it, you get negative 4. Then add another 17 until you get a positive number. That gives you 13. So that is what you see, 13x squared. Then again, this one has no common term, has no like term. So, but it's less than 17, so we just write it. It's less than 17. What about this and that? Gives us a negative 3. We are doing it mod 17, and then the answer is negative, so we add 17 to it to get a positive value. So that's how we add. Very easy. You add like terms and you make them positive. And if they are bigger than 17, you reduce them mod 17. So when you're doing it mod n, it's not something strange. We already done modular arithmetic and it becomes easier for us to do that. Let's see how to multiply again. We just do the same way we were multiplying before. After multiplying, you now reduce it mod 17. You multiply it first. So we have this. Just multiply it first. This and that gives you this. Then this and that gives you that. Then this and that gives you 30, and so on. Then let's come to that. Get this. Then that gives you that. Then 15 and that gives you that. And so on. Just the same we've done in our previous examples. Then collect like terms. Collect like terms and sum them. So when you collect like terms and sum them, this one has no like term, so it's just there. Then this one is a like term to that. So when you sum them, you get this. And this is a like term to this. And that, so when you sum them, you get this. And x raised to 4 is a like term to that. And when you sum them, and so on. So after summing, now reduce this sum mod 17. Reduce it mod 17. So it's very easy, just to use the first procedure. And after you have the result, you now reduce this result mod 17. So when you reduce this mod 17, just add 17 to it until you get a positive value. So it is negative 21 plus 17. That gives you negative 4. Then plus 17, you have 13. Come to this 87. Divide 87 by 17 and get the remainder. Get the remainder. The remainder is 2. The 6 is already less than 17. 49 is larger than 17, so divide it by 17 and get the remainder. So the remainder is 15. And so on. So that's how you do it. You just multiply it the normal way. And after multiplying the normal way, after summing, and then you reduce it mod 17. So that is how you do it. It's not difficult. The next example, just the same strategy. This time we are doing it mod 6. We are doing it mod 6 this time. So let's begin by summing. This one has no like term, so you just sum it. It's x cubed. Of course, the coefficient is 1. So 1 is already less than 6, so you just write it. Then the second one, this and that are like terms. It gives you 3x squared, which is less than 6. So just there. Then this has no like term, but is negative. So you add 6 to it, and you get it 2. And then this and that is 7, which is greater than 6. Divide by 6 and write the remainder. Divide by 6 and write the remainder. So that's how you do it. So it's very easy again, adding. So let's see again how we multiply. How do we multiply these polynomials, these two polynomials? That's the same way we've done before. Using distributivity, this and that gives you that. And then this one gives you negative 10x raised to 4. Then that gives you 25. Now, so for me, I do that and then sum, then collect like terms, then reduce mod 6. But if you want, you can even be reducing it. As you multiply, you reduce it. Even this one you can reduce and write here plus 6 and then plus 6. You may write here 2, then reduce that, then reduce this, then reduce those where they are larger. Then after reducing, now collect like terms and sum. Of course, when you do that, you'll find that some summations are going beyond 6, again reduce. So that is a lot of work, but it will give you the same result. So what I mean, you can reduce it. Even this one, you can reduce them here. Even this products. You can even begin from the beginning. You can even begin just from here. Reduce them from here. So for instance, this would be 5x raised to 2, and this plus 6 would be 2x, and this will just be 2. And then this will be x raised to 3, plus 6, that will be 4, x squared, 4x squared, and this will be 5. You can even begin from there and then multiply them the same way. So this gives you, that will give you 5x raised to 5, 5x raised to 5, and you can see that's what we have. After collecting like terms, of course, if they're not there. Now, then this times that will give you 20 x raised to 4. And then this and that will give you 25 x raised to 2, 25. Of course, you can again reduce this. Mod 6, and reduce it. If 6 were to go there, to be 2, cos of 18. And this one will be 1. So you can reduce at every stage. That's what I mean. You can reduce at every stage as you progress, but that would be a lot of repetition. So that is why I like just doing it up to the end. Then at the last result, I now reduce mod 6 so that my reducing is just done once. But if you want, you can do it at every interval, but that will be a lot of work, repetition, a lot of repetition. Now, where we have very big polynomials, and because of application in the real life situation, so we need to have a program, and we are using a Rust program that can assist us do addition of polynomials and multiplication of polynomials so that we can apply it in the real life situations. So this is my code for doing, it will be doing for me the sum, doing for me the products. It will be telling me the degree of the sum and the degree of the product of the two polynomials. So supposing that my polynomial is, supposing that this is my polynomial. This is 2 constant, negative 4x, and then 5x raised to 2. So I enter it here, the main function. So I began with the constant. As the values of x increase, so this one is x raised to 1, then x raised to 2. And my second polynomial is here. The constant x raised to 1 is not there. You can see this is just 5 minus 2x raised to 2, then plus x raised to 3. So I began with constant. X raised to 1 is not there. X raised to 2 is there. Then x raised to 3 is there. Then I ask my polynomial to add. So let the sum, and this sum is where it is adding the polynomials, P and Q, where P is the first polynomial and Q is the second polynomial. Then let the product, it will be doing for me the product of the two polynomials again, polynomial P and polynomial Q. And then it calculates the degrees. So for the sum, let the degree of the sum be the degree of, of course, the highest degree of the sums of the polynomials. The highest degree of the polynomials. And then again, this one, it just be picking, it adds, to be adding the highest degrees of each polynomial. It adds those, and then it gives me the degree of the product. Now, then after that, it prints. It prints. Now, so here, what is happening here is that, you see, this was the main function. This was the main function. So this main function, when it says let the sum, when it says let the sum, the next thing is it calls on the function that does that sum. It calls on the function that does that sum. So that function that does the sum is the one that will then do it. So when it says let the sum add polynomials, so when you check here, you'll find that there's this polynomial. This is what is adding. So it calls on this function, and this function does that. That one does that. So that's how it will then be doing it, to add polynomials. So you can see what is happening here. So this is how it's then adding. This is how it's adding. Says let the maximum. So it takes the maximum element here and multiplies by the rest, and so on. It begins. This is mutable. So it means after every multiplication, it pushes the result. After multiplication, it pushes the result, and so on. And then finally, it has the final result after all the multiplication. Or this is addition. After all the addition has been done, so it takes the coefficient, those which are like terms, then it adds the like terms, and every time it pushes that result. Then finally it gets the final result. And the final result is here. Then the part for multiplication, again, the part for multiplication, this is where it's multiplying. And then the part for the degree is here. The part for the degree is done by this function. So this is a function that, so let me just share the code first of all before we explain how it works. We share the code for that. So this is my code that it does addition of polynomials. So in the main function, my polynomial is here. My polynomial was, this is the polynomial 2 minus 4x, then plus 5x squared. So you can see I've entered my p, which is a polynomial, beginning the constant, then x raised to 1, the coefficient of x raised to 1, then the coefficient of x raised to 2. Then here, the constant, coefficient of x raised to 1, coefficient of x raised to 2, then coefficient of x raised to 3. So you don't need to add here 0. You don't need to add 0 here, because it already knows that we've arranged these things, beginning with the constant, then the coefficient of x, then the coefficient of x squared. So when it doesn't see the other value, it knows that that value is not there. But now for this one, you have to add this 0 because you begin with a constant. Then it will ask you, what about the coefficient of x? What about the coefficient of x squared? And then if you want to have, if you have the coefficient of x3, again you add. Even if you have the coefficient of x raised to 4, you can still add. Now let's run this code and see what the result is. Now, so when you run, it's running, let's see. Okay, it has run. So after running, it tells us, and again, it has arranged them in the order we arranged them above here. In the order we arrange them above. Above here, we began with the constant, then followed by x, then followed by the coefficient of x squared. So that is what is arranged here. At the bottom here, you can see that the sum of the first polynomial plus the sum of the second polynomial, or the sum of the first and second polynomial, this will be the constant, 7, then x, the coefficient of x, then the coefficient of x squared, then the coefficient of x cubed. So it has arranged them in that form. And again, we have for the product. For the product, the first one will be the constant. The way you arrange them here, so that is the way it produces. So if you reverse the arrangement, then again, this will be reversed. So this will be the coefficient of the constant, of course, then the coefficient of x, the coefficient of x squared, the coefficient of x cubed, the coefficient of x raised to 4, and then raised to 5. The raised to 5, because when you multiply this x raised to 3 by this x raised to 2, what you get is x raised to 5. So that is why you see it goes up to there. And then after that, it gives you the degree of the sum, then the degree of the product. Okay, I also have a code for doing mod n. So let me again show you that. So if you want to add polynomials mod n and add polynomials, multiply polynomials mod n, and this is the code. So again, the way I've arranged them here, you see them inside this. I began the constant, then the coefficient of x, then the coefficient of x squared. Constant, coefficient of x squared, then the coefficient of x cubed. Now the rest are just my notes. So this is the code. Of course, I'll share it in the notes. So let's run this and see what we get. So it's running, it has given us the results. So what I was doing it mod 6. The example of mod 6. So let's go to our main function. This is where I put, look at this. I've said, let the sum add the polynomials mod 6. You can see the mod 6. Then let the product multiply the polynomials also mod 6. So this is where you put the n. This is where you put the n. So when you multiply, when you run the code, it brings you these results. Okay, so that code, this other code is here. So I'll add it in my notes and then I send the notes just in a few minutes time. I want to stop there because of time. Let's stop there so that we meet on Monday in the evening.